purpose of this lab is to see how different substrate concentrations affect the rate of reaction in enzymes.
The yeast spheres will represent the enzymes, and the hydrogen peroxide will represent the substrate.
The yeast spheres are broken down by the substrate hydrogen peroxide, and oxygen is released for the yeast spheres to
To
rise.
prepare our yeast spheres, you will need sodium agglutinate, calcium chloride, and 10% yeast.
To prepare for our lab, we're teaching you how to make yeast spheres, which will represent the enzymes. To begin, we need to mix 10% the yeast solution with 100 milligrams of water, which we have previously done.
To make the yeast spheres, you need to take 1 milliliter of sodium agglutinate and then 1 milliliter of active yeast.
Mix the solution in the syringe.
Then slowly drop little drops into this calcium chloride, and you'll see the yeast spheres begin to form. The calcium chloride makes a outside shell around the spheres.
This is because the yeast and agalute reacts with the calcium chloride, forming the outer shell, which creates a lining to keep the liquid inside the spheres enclosed. The spheres will set quickly, so be careful when handling them not to pop them.
We have our negative control and our positive control. The negative control is water, and the spheres will not rise in them, but the hydrogen peroxide will cause the spheres to float.
The sphere will sink to the bottom of the cylinder, then a catalase produced by the yeast reacts with the hydrogen peroxide to form O2 gas bubbles around the sphere. This causes the spheres to rise to the surface. The more concentrated the hydrogen peroxide solution is, the faster the spheres will rise. The water will not rise because it has no oxygen bubbles forming around the spheres, so they cannot rise to the surface.
Once the yeast spheres are made, gather hydrogen peroxide, water, napkins in case of a mess, and 4 graduated cylinders. Pour 50 milliliters into one cylinder and call this 100% concentration of hydrogen peroxide.
Fill one cylinder with 50 milliliters of water, which will be your negative control. Fill another cylinder with 25 milliliters of hydrogen peroxide and 25 milliliters of water. Finally, fill your last cylinder with 40 milliliters of hydrogen peroxide and 10 milliliters of water.
Once all of your cylinders are ready, take the yeast balls and drop 5 into the first cylinder made. Time the amount it takes for the yeast spheres to rise and record the data. Once you have done this, repeat with the rest of the cylinders. Do 3 trials of this process as a way to enhance your data.
For each graduated cylinder, take the average of the 3 trials and put them into a table like this.
The average will help you make a box and whisker plot so you can see if your data is significant or not.
If you look at the average time it took between the 50% hydrogen mixture and the 100% hydrogen mixture, the whiskers overlap between 5.2 and 7.4 seconds, which is not good. It means there's no real significance between the data and that we don't have enough evidence to say if it was a substrate concentration or not. And then comparing the 50 milliliter hydrogen peroxide with the water-based solution, there's very significant difference because the whiskers don't overlap.
And overall, the lack of significance here needs to be backed up by the significant data set between this one and these two, which do prove that substrate concentration has the true effect.
Enzymes, as shown in the graph, will react more quickly the more substrate they have. And this is true for all higher percentages of substrate because only so many enzymes can bind with them, which is why the reaction rates were similar. But then the lower concentration of substrates cause the enzymes to react much slower with a significant difference in the graphs.
The lower the concentration level, the slower the reaction time of the enzymes work.
The science behind this is the more substrate there is, the faster the reaction is, but at a certain point, the enzymes will run out of substrate and the reaction rate will slow.
An example of this is that lactose intolerance is that an individual can't break down milk or lactose in the stomach because there isn't enough lactase enzymes.
An example of how lactose intolerant people can deal with this is consuming things like lactate, which insert enzymes that break down lactose in the stomach and help them be able to break down the substrate.